Hi. Oh, yeah, you can. I think I'm okay. So, yeah.
So I can
Thanks.
just leave?
Yeah, if you or if you want to listen, you
Okay. I might just leave.
sure. Yeah, yeah. Okay, let's start. So um, last time we had started on kind of two kinds of on how do we begin to process digital information. Prior to that, we kind of looked at how we represent and what kind of trade-offs occur. And when it comes to processing digital information, I kind of mentioned and introduced kind of the very broadly two kinds of digital systems you can imagine. One, which I call combinational systems, are those which don't have any memory. In other words, their output at any given point in time is strictly a function of the current inputs. Now, this is a mathematical idealization because in reality, any system, any circuit has some delays. So the output at any given point in time lags or depends on inputs a little bit before. At the very least, you have speed of light limitation, but more generally, transistors and all have some additional delay. And I guess in modern technology, we're talking about like nanoseconds or maybe tenth of a nanosecond, something like that, and higher. Okay, so I had this example of like a comparator which compares to temperatures, current temperature coming from a sensor and another temperature which is set by the user. And then it outputs a 1-bit value, fan on off, which controls a fan through, let's say, some sort of a relay or something like that. And this is an example of a combinational system because barring those little bit of delays, at least ideally at all times t, it is the case that output is equal to input, the two inputs, the comparison of the two inputs. But that leads to the second type of systems which have memory. Now, that's true for us in general, right? I mean, given the same input, we don't react the same way because we also in our brains, our brain has pretty large mental capacity, storage capacity. So we always look at the input and then we process it together with whatever the bits in our brain are, right? I mean, you can think of that as a state of the brain. So sequential logic brings that notion of memory. So kind of the idea now being is that let's imagine we are designing sort of a logic for a calendar, and it is something along the following, that I have input, which is sort of today's month, today's day of month, today's day of week, and they're, let's say, being displayed on some sort of a display. And then I'm always computing tomorrow's month, tomorrow's day of month, tomorrow's day of week, and we are going to do it at some sort of a clock tick. Okay, so at midnight we want to roll over, right? I mean, so again, think of the system as a display. It's displaying today's date at the clock tick. When the clock tick comes, we want it to roll over. So something like this, you could imagine that I need some sort of a magical block here, where at midnight there is some sort of a signal which comes in. Think of it like a pulse or an edge, like a 0 to 1 transition or a 1 to 0 transition. However we define it, there is some sort of a thing which indicates that it's midnight. And then at that point in time, we want to update the display. Okay, so in this part, and not at other times, right? I mean, so at all other times, if this blob were to be some sort of a combination logic, like one shown out here, then it always takes today's date and it updates that tomorrow's date. But if this yellow block was also combinational, then we have a problem, because it would also immediately update its output. So what we want is a block which only does things at certain moments in time, right? I mean, and at all other times, it doesn't depend upon what is at the input. Okay, so it kind of acts as a block. So think of it in the following way, that this is like a memory of some form. It's a storage area. And when the tick comes, then it takes whatever is on the input out here and puts it into the memory. And then the output of this memory at all times is following the content of the memory. Okay, so again, kind of like a room, or whatever, something whose output always reflects what's inside that box, but the content of the box are updated only when an edge comes, and at no other time. So if the midnight signal is 0 or 1, it doesn't have any impact, but at the moment it changes, we want to update this. And then after that, it's okay, because this guy is a combinational logic, and then it will compute the tomorrow. So it will compute tomorrow's date a little bit after the midnight tick, but its effect won't be felt on the yellow until the next midnight tick. So these kind of functions, they're not behaving combinationally. They are no more dependent upon just what is on the input, but they kind of depend upon when did this tick come, right? When did something happen? So that's an example of sequential systems. More broadly, you can just say that, look, any system where history matters, I can't just compute an output at all. I can't just write output at time t is equal to input at time t. I have to know something else. So midnight in this particular case is this clock signal. Sequential systems usually have some sort of a timing signal when things happen, okay, when memories are formed. Actually, even our brain has like that. Deep inside our brain, there is actually a clock which ticks, which kind of essentially acts as the pacemaker for the brain. Okay, so when it is midnight, it triggers something to happen in the yellow box. Output does not reflect the input unless it is midnight. At other times, the output is just reflecting what is inside the yellow box. So yellow box has therefore a storage area, or in computer parlance, it has a memory. When you write a program, your variables are corresponding to memory, your files, that's a more persistent memory, but they're all memories of some form. And you can imagine that every time your program runs, then the output can be a function of the state. So like, for example, if you have programmed in, let's say, C++, then you can have variables inside a function where if you put static in front of the variable, then the value of that variable is remembered from one run of that function to the next run of that function. And so, so in that example, every time I run the function, it can potentially output a different value for the same input. Or, for example, your function may make use of global variables, variables which have the scope of the whole file. Again, that would be an example where my function, every time it runs, given the same input parameters, it can potentially output a different value. So, so we see that in software quite a bit. In hardware, it becomes more explicit. We need some place to store those variables, those memories. And in this case, I've kind of abstracted it as this yellow box, where at the tick, the content of the memory is updated. At all other times, output is reflecting the input, reflecting the content of the memory. So, yeah, so that's kind of the idea behind sequential. We introduce some sort of a memory element. Okay, so this special circuit, you'll see a lot of it in this course, is referred to as register. There can be other ways of, there can be many different ways of implementing this memory. Very commonly, it is done using something called flip-flops, but there can be other ways. But in an abstract way, you can think of it as that it has some input signals, some output signals, same number of bits. So in this case, like I'm showing 3 bits of input, 3 bits of output, and memory is equal to when the clock ticks, and very commonly we consider the clock ticking when there is an edge in the signal. So clock is also a digital signal, it's a bit 0, 1, but because it's a timing signal, we give a special attention to when it changes. And so clock signals are shown with this triangle. And if this kind of a signal means that the clock ticks when it is rising. If on the other hand, it was drawn like this, there's a bubble, then means the clock ticks when it is going down. So this this one is called rising edge, and this is falling. Depending upon, like usually within a system, you will have everything falling or everything rising, and that's kind of the pacing the system. So register has this memory. Memory captures the input when the clock ticks. In our example, when that rising edge comes, and output is otherwise equal to memory at all times. Okay, so output always reflects the content of the memory, but the memory is updated whenever the clock tick comes, and at all other times, memory is stable. Okay, so it's kind of a magical circuit of sorts in a way, because how do we implement? How do we make it kind of at that tick? And we'll see later on how that happens. But for now, imagine that we have such a box available. So now we have 2 kinds of primitives, right? Primitives where output always follows the input. Input changes, then modulo some delay, output is some function of input, and then all sort of memory we kind of set it aside into this kind of a register where output always reflects the memory, except and the memory is updated. Memory captures the input when the clock tick happens. So very critical block. So I just want to make sure no questions on this one. Everyone comfortable with this idea, right? Tick comes, input gets dumped into memory, output reflects the memory all the time. Okay. So, so now, if we have such a thing available, then that digital calendar I had talked about is easy to do. I just have to make sure that my clock ticks every midnight. Okay, and I can make it using the register and this combinational circuit, which is computing tomorrow. Now, computing tomorrow is kind of a little bit messy, right? Because we have to worry about rollover at the end of the month. We'll have to see which month it is. Based upon that, we will do the whether we have to increment day of month, day of week, always increment. So that's okay. So you can imagine if I were to give you some way of adding things and some way of making decisions, you can implement this kind of a thing, right? I mean, so tomorrow's I guess we'll have to deal with all the months with 30 versus 31. We'll have to deal with February. I guess in this case, we don't have years, so we can't do leap year, but you can write a mathematical expression relating all the three outputs to all the three inputs. And it would be like in a programming language, you could write it using kind of a conditional clause of some form, for example, depending upon the programming language. So this can indeed be done. This is a purely combinational function. I can do it via lookup table, right? I mean, I can create a truth table where inputs consist of these. So 12 bits of input. 12 bits of input is 2 to the power 12 rows in my truth table. So 4096 rows. And then I have again 12 columns. So I can certainly create a truth table, and so anything which can be done in a truth table, we know that it's a combinational logic. So this is combinational, this part, and we have this register. And then how can we get the clock? Something which comes only at midnight. So in computers, we have clocks which run at some frequency. Usually in our PCs and all, our clocks nowadays are some gigahertz, right? I mean, I guess typical modern laptops are probably around 4.5, maybe 5 gigahertz. If you have a low-end thing like Raspberry Pi or something like that, maybe 1 gigahertz, 2 gigahertz, something like that. How are these clocks generated? Anyone? Where do they come from? Piezoelectric. Yeah, that's so anyone knows what piezoelectric is? And someone else? Piezoelectric. Okay, piezoelectric. Okay, so I'll let you answer. Go ahead. Right. So piezoelectric are certain kind of crystals made of some special material, right? I mean, quartz crystals specifically. And when you well, so they can go both ways. You apply a voltage, then they vibrate, and you apply mechanical force, they produce voltage. So you can use in whichever direction. So essentially what we do is, in this case, we kind of apply voltage to it, they vibrate, we extract that frequency, you go through some circuits, some filtering process and all to extract the frequency of interest. Very critically, these piezoelectric, they're crystals. And if you recall your physics chemistry, crystals have multiple different planes. So the vibration frequency depends upon the interplanar distances. So each crystal, depending upon how it is fabricated, has certain resonant frequencies. Resonant frequencies are what? Anyone? I know it's high school physics type stuff. What does resonant frequency of a system mean? Yeah, you're raising your hand. Yeah, go ahead.
Like when the object that vibrates, with it loses as low energy as possible.
Excellent. Yeah. So resonant frequency is where the system, if there was no resistance, friction, and all, can keep vibrating forever, and it gets its peak energy there. So any mechanical system would have that. You can calculate these given kind of knowledge about the system. So these crystal oscillate, these quartz crystals have certain resonant frequencies. So when we apply voltages to them, they vibrate, and we get a signal which has a bunch of these resonant frequencies, and they're harmonics, they're multiples. And then using some other circuitry, we kind of extract the one where there is most energy, or the one which we are interested in. So which is why when you go and try to buy quartz crystal oscillators for your circuits, if you're making a PCB and all, they don't come in arbitrary frequencies. They come at frequencies which correspond to resonant frequencies of the quartz crystal or their harmonics. There are other ways of making these crystals also now. So now we have, just like I talk about We can make transistors on chips. You can make mechanical structures on chips. You can make tuning forks and stuff like that on chips, literally like little beams and stuff like that. It's an area called micro electromechanical systems, or MEMS. So you can make mechanical structures. And since I can make mechanical structures, I can make tuning forks. And again, recall your physics, tuning forks vibrate, they have tuning, they have certain resonance frequency. So there are now ways of making on-chip clocks without using quartz crystals. And actually, iPhone uses many of these. The reason is because I can make them on-chip. I can make them super tiny. Quartz crystals kind of stick out on the PCB and all. So, and of course, you want to integrate things. So that's the other technology that has emerged. And that one, since I can custom design the tuning fork, so I can custom design its frequency, and I can play some additional algorithmic games there. Yeah, so we are now in the era where we can get whatever frequency we want if you're willing to go down that path. You seem to be, do you have a question? No. Oh, okay, go ahead.
So for the force blocks, actually, would they have a second crystal that measures the resonant frequency of the first crystal?
No. This is done through some passive electronic circuitry. So like you make some amplification circuitry where your amplifier has a particular area, like which frequencies it will pass through, and those are which. Yeah. Any other question? Yeah, go ahead.
Wait, so the quartz crystal and then they're for clock, right?
They're for clock.
And then so what about you said about the clock?
Flip-flop is some memory things separate. Yeah.
So, like my clock changes automatically, my computer changes automatically from daylight savings stuff like that. Like how, what cost is the same to for that?
Okay, excellent question. What happens in your computers is that it is actually exchanging messages, assuming you have an ordinary computer like it's exchanging messages with what are called as time servers, which are special computers. And essentially your computer sends a message that responds. The transmit time, receive time, everything is timestamped. And then using that, you kind of compute how much is your clock offset from that time server. Now, how do time servers get their thing? So usually these time servers get their time one of two ways. They may either have atomic clocks, which are set and can remain set for a while, or alternatively through GPS. So usually we think of GPS as global positioning system, but it's actually positioning and timing system, because what it does is it finds your position in a 4-dimensional space of 3 dimensions of time and 3-dimensional space and time. So GPS lets you compute your time with reference to a set of atomic clocks up in the satellites to around 50 nanosecond accuracy. Okay, so that's how they get. And like, for example, on campus, there is a time server called time.ucla.edu. They're usually called this time.something, this time.apple.com. So your computer, I guess in case, I don't know what you have, but like Apple computers go to time.apple. Yeah. Okay, now one thing I didn't say is I said this clock only comes at midnight, and quartz crystals and all are in megahertz and tens of megahertz, right? So we also need some circuitry to multiply clocks, right? There is no such thing as gigahertz quartz crystal, and yet our computers operate at gigahertz. And here we wanted a clock signal every midnight, which is whatever, I have to divide down the clock. So then that can be done actually using flip-flops. We'll see later in the course, but there are ways using digital circuits where I can take something like the following. Let's say let's say this was my clock. Let's say it was ticking every, I don't know, 1 microsecond. So then divide by 2 would be a clock which looks like this, going half the rate, right? Every alternate edge. And multiply by 2 would be a clock which goes that. This can be done This can be done totally digitally using actually the very same registers. This one requires some analog gates. It requires using a type of circuit called as phase lock loop. And those of you are into analog circuits, you may even see it in some course. So multiplication requires some additional stuff, more complicated. Division is relatively easy. And now the reason all of this exists is because our systems have many clocks, right? I mean, if you think about like your computer has HDMI and USB and your screen, all of them require clocks, and radios, right? They all require clocks at different frequencies. So the clocking part of your digital system is very complicated, both in hardware and in software. Linux and Mac OS X and Windows have pretty complicated subsystems for maintaining time, synchronizing time, the question that you were asking here, all of these things. So it's kind of a more, let's say, it's a topic which is more specialized. So basic courses don't cover it, but super important. And actually, interestingly, there are all sorts of interesting effects also. Clocks at high clocks are affected by relativistic effects. Clocks run slowly when you go to Denver or Mount Everest. When you send clocks to satellites, they change. All of these things have ramifications. They're even in simpler things. If I'm sending you bits over the airwaves, and I tell you my bits are a microsecond long. So every microsecond I'm going to flip the bit, but I have a clock of my own from which I'm measuring that 1 microsecond. You have a clock of your own from which you are measuring that 1 microsecond. If we have a difference, then soon we will drift apart, right? Because my 1 microsecond is not quite the same as your 1 microsecond, or kind of stepping back up. So there are complicated issues, but for now, let's imagine they're available to us. Okay, so 0 to 1 edge every midnight. And I guess I already talked about this, so I'm going to skip this stuff. But the clock signal itself, designing these is kind of, yeah, actually, I'll just spend some time on the slide. So basically what happens in typical digital systems then is that this is where we have this is the quartz crystal oscillator. Usually it looks like something like this, okay? Or if it's depending on the board, it would be separate, but it's off chip. There is some capacitors and all. Magic of all of this together with some additional circuitry results in something that is some kind of is a digital signal flipping back and forth between 0 and 1 at a particular rate. Tens of kilohertz to megahertz is typically what you will find natively out of this. Then we will usually either have a frequency divider or frequency multiplier, whatever, and then we get a signal which then gets to our processor. It interrupts the processor. You know what that means? Some of you I know are in CS33. You know what does interrupt mean in a processor system? Anyone? No? Okay. So yeah, most CPUs have a signal which coming in. Every time that signal again has an edge of some form, 0 to 1, 1 to 0, it causes that processor to stop doing whatever it is doing. So whatever program it is running in all stops, it jumps to or starts processing some special piece of code to handle that. So usually what happens in our computers is that somehow this hardware, all of this, sends a signal every so often to the interrupt line of the CPU, of the processor in your laptop, for example. And then the operating system, like Linux or OS X, they will have a little piece of code, and they know at what frequency, at what nominal frequency, this signal is coming. So it will update some variable in the software to reflect how many ticks we have received. So let's say in a very simple scenario, our hardware gets you a signal which is once every second. Then that variable will maintain how many seconds it has been. Now, it only tells you how many seconds have elapsed since we powered up. It doesn't tell me how many seconds it is with respect to our society's time. And that is where the question that he asks comes into play, which is I need some way of synchronizing with the external world. Some way I have to say that the offset between the seconds I have and the second that the humanity has is so much so that I can apply the correction factor. And that is what those protocols that I was referring to. You contact the network server, you measure what is the offset, and then report that. So, so all of that is done through these network protocol servers and GPS satellites, which basically help you give the real time that you want. And once you have that, then generating the signal every midnight becomes easy. Okay, so that's what goes. So stepping back, then we have two kinds of systems. Then combinational systems where output at all times follows the input. So output at time t is dependent only on function at time t minus a little bit of epsilon to account for physical delays. And then sequential systems, output depends on both what the input is and what is in the memory. So it's a function of both. So sequential logic, as I've written it as SL, its output, this output depends both on the input that I'm seeing as well as what is sitting in the memory. Okay, so usually what is sitting in the memory, we like to call it a state. So think of state of a system as some memory where it is storing relevant information about the past. So just to ask, say, for example, let's say I want my output to be, what will be a good example? I want my output to, let's say I'm getting, I'm monitoring cars coming in, okay? And they can be of different colors. And I want the output to be whenever, output to be 1 whenever the number of red cars that I have seen is odd. Okay, so weird system, but bear with me, right? So cars of different colors coming in, and I want the output to be high, to be 1 whenever the number of cars, red cars I have seen thus far is 1. And if it is, number of red cars that I've seen are odd is 1. And if it is even, it's 0. So what should I remember in my state, in my memory? Huh? Number of car scenes. Well, that will not tell me you're on the right track, but that will not tell me anything about the red cars, right? Number of cars. So I'm interested in number of red cars being odd, then it's 1. So anyone else want to take a stab? What should I remember at each time step so that I can make the output high whenever number of red cars I have seen thus far is odd? Okay, previous number of? Yeah, exactly. So a nice solution would be I remember the previous number of red cars seen, right? But the problem with that is it will keep going up, right? I mean, cars keep coming. But if I only remember the cars, red car, every time there's a red car, I change this 1 bit of memory from 1 to 0 or 0 to 1, right? I mean, so all I need to remember is the car seen thus far is odd or even, and I flip it every time I see a red car. Excellent. So the point out here is I don't have to remember everything about the past, right? I mean, I could certainly solve this problem by remembering the whole sequence of cars seen thus far, but that will require infinite memory, right? Because cars keep coming. But actually in this problem, I only need 1 bit of memory to be able to solve my problem. So any problem which can be solved with a finite amount of memory is called a finite state system. Okay, I only need to remember a finite number of bits to be able to solve my problem. We'll see many examples of it later in the course. So we are dealing with physical systems. So this S, the state, has to be a finite number of bits. So we are really interested in systems which are finite state. Okay, if you need more infinite state, if you need, then you need some external storage, like some sort of a large reservoir external to our system. Okay, But within the system, we are going to have a register, which has, in our case, m+1 bits here, or as shown out here. Okay, so finite number of bits. So output is a function of input and the state. And then every clock tick, I do two things. I compute the output and I update the state. If it's a clock system, I can also have sequential system where there are no clocks. Okay, so S is the memory, right? This is the memory. And this is the output, and this is the input out here. Okay, so that's the notion of sequential system. Now, combinational system, one way of thinking about it is it's a special case of a sequential system where there is no memory. Okay, I mean, essentially, I have 0 bits of memory. Okay, so that's sequential system. It has memory, and output depends upon input and state. Okay, so usually, so we have combinational, sequential. We saw that sequential systems can be built using combinational system plus the register blob. Okay, if I'm working with clocks, we'll see sort of the other ways of doing sequential system also. So when faced with our design problem, when faced with some algorithm that we want a black box system to realize, then we are going to sort of decompose it into these sequential and combinational blobs. And ultimately, we want to break it down into some really simple primitives. And those primitives are called logic gates. So logic gates are kind of like the atoms of digital systems. Okay. And actually, the registers can be made using logic gates, but in a particular manner. So we are going to see that also. So let's look at this example. So I have, again, this system. I have thermostat, there's a calendar, which is telling us what's the day of week, what Sunday, this thing compares the two. So it outputs a 1 if the day of week is Sunday. Then this guy is saying day of week is not Sunday, right? Output of this thing. So this is a function which inverts the logic. And then we are saying fan is on if temperature is high and day of week is not Sunday. Okay, so kind of this is a logic and this is a not. This is an equal function, and then I have somehow temp high and coming. So I can begin to do sort of a lot of logic problems that you encounter, right? I mean, some sort of a condition which is given and all. I can begin to express using these kind of primitives. And one thing, to any mathematical function that exists can be done using these logic primitives. Okay, in fact, any mathematical function that exists can be done just using an infinite supply of these two gates, an AND gate and NOT gate. If I give you infinite supply of AND gates and I give you an infinite supply of NOT gates, then anything which is computable, you can compute. Okay, so there is nothing that you can't do just with these. In fact, you can even do equality check using these. Okay, so this is kind of redundant. So so there is kind of some basic primitive, but of course, much like software, we often use more complex building blocks because they make our life easier. Okay, so it's not that I cannot do addition using not and AND, it's just that it will be very painful to do it. When I was undergrad, when I was TAing computer architecture course as a grad student, and when I myself was an undergrad those days, so this is 1980s, very fashionable used to be design a little processor using just a supply of NOT gates and AND gates and all. Okay, I mean, these things are kind of pointless now, but that's how we used to be tortured. Okay, so essentially, just walking you through, the output of equality is telling whether today is Sunday or not. Output of NOT gate, so a NOT gate if it gets a 0, outputs a 1. If it gets a 1, it outputs a 0 in a Boolean system. Usually, we associate 1 with true and 0 with false. It doesn't have to be. You can also say 0 is true and 1 is false, and that's fine. And also 0 and 1 we saw are represented with voltages, and we saw that 1 was represented with a high voltage and 0 with a low voltage. Again, that doesn't have to be. I can imagine a system where 1 is represented with a low voltage and 0 with a high voltage. So both these mappings, what voltages correspond to 0 and 1, and whether in a Boolean logic system true and false correspond to 0 or 1, these are your choices. Commonly, again, 1 is interpreted as true. In many programming languages, in fact, 0 is considered false, and anything non-zero is treated as true. In some other programming languages like Python, you have an explicit type called true and false for Boolean variables. So these are all kind of choices intuitively unless the problem asks for otherwise. You could say we stick with the convention: 0, false; 1, true; low voltage 0, high voltage 1. Okay. But again, yeah. So output of this NOT gate is often also referred to as inverter. Okay. So often this is called inverter. It inverts the logic sense. So it's not Sunday. Then the AND gate outputs. So in logic terms, I would say AND gate output is true whenever both the inputs are true. But since we have said 1 is equal to true, therefore, for our purposes, an AND gate is one which, if both inputs are 1, then output is 1. It is 0 otherwise. If all inputs are 0 or 1 with equal probability, then an AND gate will output 1 out of 4, 25%. So an AND gate outputs 1 if and only if both inputs are 1. And so the fan is turned on when temperature is high, except on Sundays. Okay, so that's kind of the logic formalism about it. So coping with, I mean, this is obviously a super simple design and all. So in general, we deal with much more complicated systems. So the one thing that we do is we always try to break it down into simpler steps, like with this thing. Okay, so yeah, I like this put a quote so I can stick that. So what are common type of gates? What's a building block? So of course, logic combinational functions can have any number of inputs. But of particular importance for us is combinational logic, which has either one input or two inputs. So the simplest ones. So if you think of a combinational logic with one input, right? So it's a truth table with two rows, right? Row corresponding to input being 0 and row corresponding to input being 1. How many combinational functions are possible which has only one input? So one of them is here, not, right? It takes an input and inverts it. Okay. Do you think, is there any other one? Yeah.
Yes. Like just like whatever it is.
Okay, that one has no input. So that's excellent, I think. Actually, so there's also combinational logic which has no input. It just outputs yes or just outputs no. Outputs 1 or outputs 0. So there is combinational logic which is hard-coded 1 or hard-coded 0. But what about combinational logic which takes one input? Output does depend on the input. So one is invert and the other is pass through. Don't invert. Identity. Okay, excellent. Now let's move to functions with two inputs. So firstly, how many such functions can exist? Two input and output. Okay, and the output should depend upon at least one of the inputs. Okay, so so again, if you think in terms of a truth table, so I have two inputs, so I have 4 rows. So my output column has 4 bits, and each one of them can take 2 values. So it's 2 times 2 times 2 times 2, 16, of which 2 will be trivial functions, all zeros or all ones. The remaining 14 will have some interest interesting thing. Now, not all functions, all those 14 functions have some commonly ascribed name to them. Some of them do, but others don't. So I have given some examples out here which have names attached to them. So and, which we already saw, and is both inputs are 1, output is 1, 0 otherwise. Or is if either or both the inputs are 1, output is 1, output is 0, only if both inputs are 0. Okay, so again, and would be high 25% of the time if the inputs have equal probabilities of zeros and ones, or would be high 75% of the time if, again, given equal probability distribution. XOR is referred to as exclusive OR. So output is high if one and only one of the input is 1. Okay, so it's either 1 0 or 0 1. So if both inputs are 0 or both inputs are 1, then the output will be 0. So in this particular case, output will be high half the time. You can also call it as the function which is not equal to. Okay. NAND is AND with this bubble at the output. Bubble is basically borrowing from not, is referred to as kind of an inverting thing. Okay, so it's basically saying it's an AND gate followed by an inverter followed by a NOT. So it's saying a NAND gate outputs 0 if both the inputs are 1, otherwise it outputs a 1. And then NOR is basically an OR gate with an inverter in the output. And likewise, there is an XNOR, which is an XOR gate with an inverter at the output. Yes, sir. Absolutely. So if I just give you an excellent observation, if I give you infinite supply of NAND gate, you can solve all the problems. And likewise, actually, if I just give you an infinite supply of NOR gate, you can solve the problem too. So, so just because, so now let me ask you the following. If I said I can solve all the problems, so let's start with using a NAND gate, 2-input NAND gate, can I create an inverter? You put input to both, right? So I can make, okay. And then once I have the inverter, I can create an AND gate by just putting that inverter in the output. So I can create an AND gate. I'll let you guys think about how you can do other things, but yes, you can. Just with an infinite supply of NAND gates, I can build everything, anything which is computable. Okay, so anything which cannot be done means those are non-computable problems. Okay. Yeah, and NOR gate, same story. Okay, so let me. Okay, so these things. So remember again, there are many other 2-input logic gates, except not all of them have nice names for it. XOR with an inverter is called XNOR. Now XOR, I said, is the 2 inputs. If they are different, it outputs a 1, right? One is 0, the other 1. XNOR would be the other way around. XNOR would be if both inputs are 0 or both inputs are 1, output will be 1. So XNOR is the equality function for 1 bits. Okay. So yeah, I guess I already covered this point. So any 2-input function, I can represent it as a truth table like this. And then I just have to think about how many choices I have for the output column. Each y0 can take 2 values, y1 can take 2 values, y2 can take, y3 can take 2 values. So I have 2 times 2 times 2 times 2, total of 16 possible output columns. Each one of them corresponds to a different function. One of these functions is all zeros, not very interesting. Another of these functions is all ones, not terribly interesting. But the remaining ones are going to be interesting. Some of them are just pass through also, right? I mean, output is just equal to A, or output is just equal to B, or something like that. So, so this is a listing of all the possible functions. So what I've done is think of it like each column out here, right, corresponds to some function. So like this column corresponds to some function. Okay, this column corresponds to some function. So there are 16 possible columns. All always 0 and always 1 are the two trivial functions. This column is a NOR, this column is NAND, this column is simply saying B, A, this is AND, this is not A, not B. There are some others which we didn't give a name, like A less than equal to B, A greater than B. So you can always express them in some mathematical equation, but they may not have a common name like AND, NAND. Okay, the names are for AND, NAND, OR, NOR, NOT, XOR, XNOR. These are the common names that we use. This one, anyone seen this symbol? What does that, like, you might have seen in a math course, right? Yeah. Implies, B implies A. It's an implication function. Yeah. And there would similarly be an A implies B somewhere. Yeah, here. A implies B. And then XNOR, I said, is equality. You can think of it as A implies B and B implies A. So that's a bidirectional arrow. And yeah, also, if you notice that there are many different symbols used for the same thing. So like, for example, AND is sometimes written as A and B with an ampersand, sometimes with a dot, sometimes with this caret sign. In this course, I think the TAs must have emphasized this also. In this course, we are going to stick with some certain symbols. So for AND, we are going to use AND. For NOT, we are going to use this tilde symbol. For OR, there is OR here, we are going to use the vertical line. Okay. And the reason, and I want you to stick with that, and the reason, and it's a hard requirement, mostly because when we do auto grading, we are going to assume these symbols, partly because not all keyboards have the other symbols. And so I want to stick with these. So when we, whenever we are using, kind of use these symbols. Like, for example, sometimes for OR, people use plus. We are not going to use that. So anyway, just bear in mind whatever we specify, stick with that. Yeah, question.
Use for
Pardon me?
which symbol, like, is there anything simple or like
For which one?
for XOR?
Yeah, for XOR, usually I have used symbol, caret, power sign. Yeah. Unfortunately, there's no symbol for XNOR. So yeah. And look, again, in real life, probably doesn't matter. Programming languages, those of you who are in the honor seminar, Verilog insists on some particular usage of the symbol. I think it's good to stick with things that you can type with an ASCII keyboard and not require switching to a equation editor of some form. Okay, so, but for our auto grader purposes, we insist on certain symbols. Okay, so properties of logic gate. So again, we kind of seen this thing. If I connect a bunch of combinational circuits together, what do I get? Do I always get a combinational system, right? If I give you a bunch of logic gates, let's say those 2 input logic gates, I get slap them with some wiring connecting them. What would I get? Do I get just a larger combinational logic? What do you think? Help me draw it. Let's see. So I have a NAND gate. Oh, okay. This is what you mean. Something like this?
Yeah.
Okay. But I'll still be, I'll be able to simplify it, but it will still be combinational. So essentially, think of, like, let's say I give you a mathematical function f is combinational. Okay, output depends on the input at that moment. I give you another mathematical function G. So let's say I have mathematical functions f, g, h. Let's say they're all combinational and all take two inputs. So what if I were to do f of g of x comma y, a, h of x comma y? Well, this will still be combinational. Okay, I'm just creating, I can do it. So in this example, for this type of function, it would still be combinational. But the reason I'm asking this question is because actually the answer is no. Just because I wire up a bunch of combinational, I may still end up with something sequential. And why does that happen? So the key part is if I connect combinational modules in a manner which is acyclic, there is no feedback. That is, if I go from an input, and keep traversing, I'll always get to an output. It will never be the case that I will circle back there. So this is an example where I have two combinational logic, and let's say the signals are flowing like this. Okay, so everything is just flowing in one direction. I can line up the circuit, information flows left to right. So if they are connected acyclically, no loops, then the resulting system is always combinational. But and that's it. If that property doesn't hold true, if there are loops, then the system may be sequential. Okay, it's not necessarily sequential, but may have memory in it. But for our purposes, what it matters is that if I give you a hugely complicated problem, combinational problem, right? Write for me this function of gazillion inputs and a combinational function. I can decompose it into simpler stuff. And in fact, as I pointed a little bit earlier, I can decompose it all the way down to only NAND gates. Okay, so I can always do that. So that's if there is feedback. So let's say, for example, let's say this circuit, I were to connect it like this, then it becomes, or may become, it's not guaranteed, depends on the specific thing, it may become sequential. Very generally, all the tools you work with will barf if they see a feedback through combinational logic. That is, if I can start from a point and travel, come back to the same point through only combination logic modules, then there is something deeply wrong. So now I don't want to say no one designs systems where you don't have loops. There are some very carefully designed systems where loops are present, but in normal design you will not encounter. But just to give you an example where loops can be useful. So let's take this system. Three inverters tied like this, connected. What do you think we'll do? And so again, output of third inverter fed back to it. What will happen? Anyone? Yeah, you want to take a step? Okay.
I think that the well might oscillate.
Yeah. So what will happen? This guy is 0. Let's say hypothetically this NOT gate has a delay of nanosecond. Okay. So 1 nanosecond later, this becomes 1. Another nanosecond later, this becomes 0. Another nanosecond later, this becomes 1, which is this guy. So basically it will oscillate with a 3 nanosecond. Every 3 nanosecond it will flip. Okay. So so in this case, it's a sequential circuit because it's basically saying new value is the opposite of what my last value was. There's no input in this case. So so that's an example of, yeah.
The sequential circuits begin to break clocks.
No, sequential circuit don't need to, as long as sequential circuit has the behavior that the output can depend at some under some circumstances, the output can depend upon us, upon something which happened in the past, then it's sequential. Doesn't have to oscillate. If that's the question now. Although oscillatory circuits are sequential, but the other way doesn't happen.
The can oscillating circuit created, like the one you see there, cannot be used to make a clock.
Yeah, this can be used to make a clock. In fact, on many chips, it is used to make a clock. Odd number of inverters, they will oscillate. It's a pretty lousy clock because its frequency is not very good and stable. But in many processors, when the system powers up, it initially uses a clock like this because you can make this thing on chip. It's very compact. So yes, it indeed is. And then it will switch to the quartz crystal. Quartz crystal takes some time to power up. So initially the system may just run on this kind of a LCPO clock and then switch to that. Can you speak louder, please?
You just
Oh yeah, you can make it one not gate too. I just drew 3 just for fun. Yeah, absolutely. Anyone else with questions? Okay, so acyclic stuff is the can lead to sequential behavior, and in fact, registers are those memories that remember the clock comes and the latches, it remembers the input. Those are created using NAND gates or NOR gates with feedback. Okay, so feedback or loop is the heart of enabling you to create things with memory, things which are sequential. Okay, so let's talk about a few properties of gates. Regenerative, which we saw previously, directional, separable, and closure. So what do we mean by that? So some also want to say some of these properties are not always true. So there are some caveats, but still. So regenerative basically means because of those noise margins, signals get cleaned up. Okay, so we already discussed this thing before, but basically, if my input coming in has voltages which are within the allowed input bands, but when I generate the signal, the output is cleaned up and it would comply with a more stringent thing. So the noise, so we are tolerant to certain amount of noise margin, right? So it regenerates. We had talked about it last time when I had said that as a result of this, digital systems, you can cascade them without the noise building up, unlike an analog signal system, where as you cascade them, noise builds up until it becomes intolerable. Okay, signal to noise ratio, which those of us in electrical engineering love to talk about, right? So as the noise rises, signal to noise ratio worsens and all sort of bad things happen. Okay, so regeneration or whatever suppression of noise is one property. Directional, it's a one-way thing. So a NOT gate just conveys information left to right. Signals are propagated only in one direction. Output is a function of the input. Output does not influence the input. Okay, again in a logic gate, which to us is just a combinational piece there. Okay, so input is not changed. Okay, so that's straightforward. Okay, one thing to keep in mind is that it's certainly possible that the input may change later in time as a function. So like, for example, I don't know, our thermostat example, right? I mean, the thermostat fired up your AC, the AC result ran, the temperature lowered, and as a result, the temperature sensor is now reporting a cooler reading. That's certainly possible. So there can be an outer loop. Usually our computers sit in some sort of a societal or loop of some form, right? I mean, so inputs do change as a consequence of output, right? I mean, if my system, whatever, I get an email, I act upon it, and then the input will possibly change. So I'm not referring to that. All I'm saying is, if you look at a logic gate in isolation, then input affects the output, but there is no way things flow backwards through that logic gate. Okay, separable, and that's an individual gates do not change their properties when they are connected with other gates. So what I mean by that is that if I have, let's say, a NOT gate, and let's say the output of it feeds into another NOT gate, then the first NOT gate will still do the NOT function. Its functionality is not affected by what it is connected with. Now, this is an idealization. I'm taking kind of a mathematical view out here, that this mathematical entity, the NOT gate, it still does not. Electrically, bad things can happen. Like, for example, if I take my NOT gate and then put it in front of it a very big NOT gate, which has lots of capacitance, then my first wimpy NOT gate may fail to function as a NOT gate. So I'm ignoring electrical effects that can cause problems. Okay. But as a mathematical idealization, these are separable. And of course, electrical design practices are, we design these things, we size them, and also that the separation property holds. So we make sure that if I take one module from a library of hardware blobs and connect it to another module from thing, we don't want the functionality to interfere with each other. Okay. So individual gates do not change their properties. So for example, one property of interest, which is often is that of delay. So let's say I give you the circuit where I have an AND gate followed by a NAND gate followed by an OR gate, and let's say I also tell you the delays. Okay, and we'll come to this thing later, but let's say I tell you this thing takes 5 nanoseconds. This thing takes 4 nanoseconds. This thing takes 5 nanoseconds. Then a consequence of this separable assumption is that if the gates had the delay of, if let's say my NAND gate had a delay of 4 nanoseconds in isolation, even when connected, its delay will be 4 nanoseconds. Again, it's an assumption, but we kind of go with that. So assume that they do not take more delay, they do not consume more power, all the properties remain stable as we connect them. This is to keep life simple, and then we kind of adopt conservative design practices to make sure that this thing happens. Closure. So this goes back to the property I said. If I so in mathematics, what does closure mean on a set? When we say a set has closure property under an operation, then we basically mean that if I take the element from that set, apply that operation, we get another member of the same set. So like, for example, set of integers is closed under the operation of addition, right? I add 2 integers, I'll still get an integer. Okay. So closure property for combinational logic would mean that if I take 2 combinational logic and I wire them together, will I still get the new logic I'm getting? Is it still member of the combinational set of combinational logic? And the answer to that, we saw that is no, because if we have feedback. So now it depends on what we mean. If I connect it like this is combinational. If I connect it like this to combinational logic with this feedback, right? There is loop here now, right? Okay, so we have a loop. Then I may get something which is no more combinational. Okay, so combinational logic, if I give you a set of combinational logic and apply the wiring operation, then I may get something which is no more in that set. Okay. So this is cyclic, and in general, this would be sequential, although there are special cases depending upon what precise thing the combinational logics are doing, that it may still be combinational. But generally speaking, like for example, if I give you this, okay, this is actually what is called as a NAND latch. It has memory in it. Okay, and because of this feedback, so we'll see it later in the course. So except in very special cases, it's not. So under acyclic wiring, it's closed. Under cyclic wiring, wiring that may be cyclic, I may no longer be. Okay. Sequential logic we saw has both history, the output depends on history and current input. I also talked about we are interested in things where the information about history that we need to maintain is finite, right? We can't just afford to maintain every input we have ever seen. I mean, that will require infinite amount of memory storage. So we are interested in systems where we need to store a finite amount of information about the past. And usually we design these systems so that we need a clock to pace the system. That's usually almost like 99.9999% of digital systems are like that. So we will limit ourselves to those. All those systems without clocks, they are called as asynchronous systems, are also used for certain purposes, but we'll not be touching those. This is an example circuit of a 1-bit register with a clock edge. So this I will not go into why it works, but at a rising edge of a clock, it will behave the way I described. That is, it will remember what was in the data, and then this output Q, this output Q behaves like that. That Q is whatever is remembered, and what is remembered is updated whenever there is an edge. So this messy looking circuit, it actually, if you notice, it has that back-to-back NAND gate. It has 3 of them. Here, here, and here. And somehow the composition, this magic of these results in that register. Yeah. Why is it what? Why does one of them have 3 input? That is to get the clock going. That is what results in the clock edge. Remember, we want things to happen at the edge of the clock. So this one helps achieve that purpose. I'm not going to dive into details of this thing. It's way too early in the course for doing it anyways. But if you are interested, come and talk to me. We can then work through it. But it achieves that edge, a register which is sensitive to the edge of the clock. Okay. Any other questions? Okay. So how are we doing in time? Yeah. Okay. So in summary, we want to make complicated systems by partitioning them. Our building blocks are those logic gates. Without proof, I have asserted that those 2 input gates are sufficient for doing anything. We'll see shortly why is that the case. There are certain properties we kind of assume. Regeneration, which is cleaning up the signal, unidirectionality, input affects output, not the other way around. Separation, when I connect circuits together, the properties still hold, and closure. All of these things serve together to help us create a way to design more complicated systems. And sequential systems are then implemented by carving out all the memory stuff into the state register. Okay, and then building using that. So the sequential systems we'll look at later in the course are strictly going to be the ones where the only memory we have is this register with a clock, and everything else is combinational. Okay, we will allow the state register to have any number of bits as long as it is known a priori and is finite. So like at design time, we can say, I have 1,000,000 bits of state. That's fine. Modern processors probably have few tens of thousands, maybe 100,000 bits of memory. And this is excluding like cache memory and stuff like that. So that's fine, but can't be infinite. And so any cycles are all inside that register. We are not going to allow for any cycles in the combination logic outside the system, outside those registers. Okay, so let's do the following. Let's take a 5-minute break, and then we'll start on the next.
I wasn't sure. Like, why not really gains and they're not really
But
One thing is, and if you have like sequential circuit going into the sun, do you ever get effects where like if you have like small amounts of air, it propagates a bunch of times, so like the circuit doesn't mistake or
so if you have that kind of feedback, okay. And if you get into that middle zone where it's neither 0 nor 1, then there is a possibility that the whole circuit goes into a weird analog state. So not error propagation, but it can go into the metastability states where essentially it's in a non-digital domain now and remains stuck there forever. And then you have to power up the system. So this is called metastability failure. Yeah. Okay. But if the error is within the noise margin, then it gets suppressed.
the noise margin still applies even if the
Yeah.
circuit is sick.
Yeah. Because at every stage we're still going through these logic gates, right? I mean, so
Yeah.
it's just that, yeah. Okay, let's resume. So next up, we are going to go into what's the mathematical machinery. I guess I'm making it sound more fancy than what it is. It's basic, some of it that we use behind this, and it's called Boolean algebra. It's basically algebra dealing with Boolean Boolean values. Okay, so the father of this thing is, as you might imagine, a guy called Boole, lived in 1800s, and he has, to his credit, sort of this grand thing called the laws of thought. And Boolean algebra is kind of part of that. And essentially, it is what is behind computing and information theory and things like that. And kind of a lot of interesting things happen, right? I mean, the whole sort of logics and all emerged, like Bertrand Russell's stuff and all. Then in 1930s, computer science got its going with Gödel and Turing and also some of the very key things. You may have heard about these kind of things, like Gödel showed that within any sort of axiomatic systems where you have axioms and then things, any logic system, there are statements whose validity you cannot prove within the system. So you can't show whether those statements are true or false while staying within that system. Turing laid the foundation of what does it mean for something to be computable. So he kind of described this abstract machine, which works with kind of an infinite length ticker tape of sort, and so it can read and write to that tape. And then the core of the machine looks very much like what we're doing, which is it has these registers and combinational logic, and it kind of steps through things. But the main thing is it has this infinite tape which provides it with infinite memory, and with that, you could show that anything which is computable can be done on that Turing machine. By the way, just I don't know, some of you are computer scientists, so anyone knows an example of some problem which can't be computed?
We took this in like 35 last quarter.
Okay.
Like NP complete problem, I would say.
No, not NP complete. NP complete can be done. It's just that it takes a lot of time. But incompleteness.
Yes.
Yeah. Okay.
Like, for example, a compiler that could automatically determine the errors.
Yeah, or a simple one is, I give you a program, and can you write me a program which given can you write a program which given as input a program, tell whether that program will stop or not? Okay, so that's a so-called halting problems. There are problems which can't be solved. Okay, now contemporary to Turing, there was a guy called Church who gave an alternative perspective on what does it mean for something to be computable, and in terms of something called lambda functions. So his sort of approach was more in terms of function, thinking of computing as functions and applying functions, whereas Turing's approach was closer to the hardware view, if you may, which is there's a machine with states and it's doing stuff and it's reading and writing from these tapes, and the computation happens because of that. But all goes back to Boole. The other, I guess, sort of person in the story behind is a guy called Shannon. Again, I'm pretty sure at least some of you have heard of his name, because he's the guy who gave us information theory, Shannon information theory. He also gave cryptography, formalized cryptography, and did a lot of other cool stuff. His master's thesis was basically showed that electrical, by applying Boolean algebra to electrical relays, you can create logic circuits. Okay, remember this was pre-transistors, so there was no transistors. So at that time, we used relays and valves to create circuits. So essentially showed that Boolean algebra could be used to construct logical numerical relationships, and can essentially be used to make computers, at that time electromechanical computers. Okay, so and nowadays, I mean, like a lot of stuff that goes on, there is always there is an information theoretic way of sort of examining these things. Okay, so let's talk about what is this Boolean algebra. So it's an algebra where variables can take values which are binary, two values, 0 and 1, true or false. Okay, so usually, as I said earlier, we indicate true with 1 and false with 0, but again, doesn't have to be. It could be any two values, apple and orange, and I can define that could be a Boolean algebra. Okay, much like any algebra, it has variables which are represented using what are called as literals here, such as x, y, kind of they're like the variable names in your programs. Okay, so in this Boolean algebra, like in our regular algebra, we have addition and multiplication and inversion, like minus sign, for example, these kind of things, right? So these kind of operators, we have the same thing out here. So Boolean algebra has three operations. There is an AND operation, which is referred to as conjunction, right? Or product. So it plays a similar role as multiplication in a regular algebra. OR operation, which is referred to as disjunction, which plays the same role as addition in our algebra, regular algebra. And then the NOT operation, which is the complement operation, which sort of inverts, so goes from 0 to 1 or 1 to 0. Okay, so you can think of it as algebra modulo 2. So 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 1 is 1 plus 0 is 1, and 1 plus 1 is 0, and so that's an XOR operation. So addition, arithmetic addition modulo 2 in this case would behave like an XOR, and so forth. But main operations really we think in terms of as these three: AND, OR, and inversion, and they are written in these terms. For our course, we are going to use this row. Okay, and work for as ampersand, or as the vertical bar, and not as this tilde sign. Book uses this, which is more from the formal logic side of things. So unfortunately, this is these symbols don't really exist in our keyboard, so I want to stay away from those. And then other places you will see this. In fact, a very pernicious one is sometimes people just write XY to mean X and Y. Those are then very ambiguous, because what if I have names which are more than single letter? Okay, so we are not going to use these. Okay, so this is out, this is out. Okay, you stick with M16 notation. So each one of these operations, because essentially they are just like our combinational logic functions, so I can write truth tables for them. So it's kind of obvious. So I'm not going to belabor those things. They correspond to our AND, OR, and NOT gates. Okay, so yeah, so I really want you to use, just can't emphasize enough, I really want you to use this notation. Okay, so much like in programming languages, we have seen that what happens if I write complex expression, I need to somehow prioritize these operators so that the meaning is unambiguous. So so firstly, just like programming languages, we allow for parentheses to couple things together, and then the priority is not has the highest, parenthesis has the highest priority, then not, then and, then or. Okay, so for example, if I write this, and then it will evaluate to this guy first, then this guy, then this guy, and then finally the OR. Okay, so you need to be comfortable with these things, because if you get the priority wrong, then of course it will evaluate to something totally different. Okay, when in doubt, put parentheses. Okay, that's what I like to do. I mean, unfortunately, our brains are too tuned to regular algebra with plus and multiply, and that can complicate things. So stick with this. There are secondary operations that exist, and so There is implication operation, X implies Y, which is really equivalent to this. Okay. Exclusive OR. Remember, exclusive OR was X and Y are not equal, then it's high. Okay. Equivalence, which basically says it's the X NOR. It is X and Y are equal. So these are also common functions. I think programming languages of and Verilog, they do have symbols for XOR. Generally, I think whenever I do autograders and all, I allow for that, but it just complicates things. It depends on the problem, but at least a symbol for that exists. For equivalence, there is no convenient symbol to use. So unfortunately, generally you can't use it. And likewise for implication, because these arrow and bidirectional thing, they don't. I guess for equivalence, you could use programming language type thing like this, X equal Y, and that could stand for it. So I mean, there, depending upon context, you can kind of try things. So I've seen this plot before, table before, so I'm going to skip these. Okay. So Boolean algebra concepts then. So essentially all variables in Boolean algebra are taking values from zero, the set, some sort of a two-valued set, typically 0 and 1. We can name variables much like we name variables in software, and we can index variables like x1, x2 like this. Okay, so we can because oftentimes in digital systems we have like what are called as buses, like multi-bit values, like an integer or data being fetched from some other place, some memory or something. So it might be like 8-bit, 32-bit, 64-bit, something like that. So indexes are useful. So much like that. Some languages also allow notations like x3:5, kind of a slice. So it could say all the bits going from 3 to 5, for example. Boolean literal is a variable. Usually in Boolean algebra, people like to stick with single letter variables, but there's no hard and fast rule. Its complement is tilde x. If x is multi-bit, then tilde x would mean all the bits are inverted or complemented. Boolean space. So if I have a Boolean variable which is single bit, then you can say it resides. It resides in a one-dimensional space where there are 2 points, 0 and 1. But if I have a Boolean variable which is multi-bit, or if I give you a set of Boolean variables like A, B, C, each one of them 1 bit, then you can think of this A, B, C as residing in a 3-dimensional space. One axis representing A, another axis representing B, a third axis representing C, and along each axis you have 0 and 1. So much like we do with our regular things, right? I mean, if I give you 2 variables x, y, then I can think of it lying in a plane. If I give you 3 variables x, y, z, they reside in a 3-dimensional space. So so if I give you a set of n Boolean variables, then you can think of them as representing points in an n-dimensional Boolean space, each axis having 0 and 1. So so an n-dimensional Boolean space has 2 to the power n points. And any given assignment of values. So let's say I have A, B, C, D as 4 variables, then A, B, C, D represent a 4-dimensional Boolean space. There are 16 possible values because there are 16 possible points in that space. So at least mathematically, so that's the concept of Boolean space. Each axis 0, 1. Okay, Boolean functions. Boolean functions, just like our regular functions, take a bunch of input and produce a bunch of output. In particular, we are going to focus on functions which take n inputs and produce a 1-bit output. Okay, so we are interested in functions which take n, they have n input parameters, n input arguments, uppercase n, and then they output one bit. So like, for example, our 2-input AND gate takes from b square to b, right? It goes from a 2-dimensional Boolean space to a 1-dimensional Boolean space. In general, so like, for example, if I have a function of 3 inputs, a, b, c, then it is going to go from b3 to b. And in b3, it's a 3-dimensional Boolean space. There are 8 possible points. That's what you list out here. Okay, so you can think of a Boolean function then as a mapping between, in this case, from b3 to b. So every point in my b3, 8 points, is being mapped into one of the 2 points in the 1-dimensional Boolean space, right? So it's a map. It's a one way of uniquely mapping for every point in the input space, in the input domain. So input space is referred to as a domain, to output range. Okay, this is, you would have seen in your algebra, domain of a function, range of a function. You probably are familiar with concepts of many to one functions, on two functions, so on and so forth. In this case, since we are going from a larger space, generally speaking, to a single one-dimensional space, so many to one, right? Many points will map to one of the points. So, so there are various ways one can think about these Boolean functions, and depends upon what you think of as these ones and zeros. In the textbook, one way they kind of think of it is that you can think of this Boolean functions generally, as a game, and then you can think of each variable, input variables to the function, as representing a player, and the player sort of gives an input, head or tail, and then depending upon that, there's a binary result which tells whether they won the game or lost the game. Okay, so there are a variety of ways. So for example, we can say that for a 3-input function, we can say the player has to toss the coin 3 times. That will give the 3 inputs. And then we can say, when does it win? So for example, I can say output is 1. If my function says output is 1 for 1, 1, 1 and 0 for other cases, then we'll say the player will win if it gets head in all the flips. Okay, so you can, so nothing deep about it, but if you like to think of it like this, that 1 means winning, 0 means losing on the output side, and on the input side, 1 means head, 0 means tail, and I'm just tossing a coin. But whatever works. So what matters more for us is I can summarize all of these things always as a truth table, right? So if I give you a 3-input function, then I'll have 8 rows, and then my column would represent what happens for each row. And how many 3-input functions are there? How many distinct possible 3-input functions exist? Huh? Nope. No. 2 to the power 8, right? Because I have 8 rows. Each column represents a possible function. And since there are 8 rows, so each row can take 0 or 1. So there are 2 to the power 8 possible ways I can write the output column. And each one of them represents, right? So 2 to the power 8 possible 3-input functions. Okay. So I can always write things at truth table. So truth table, as we discussed last time, takes a lot of rows to write down. It's not very compact. It's hard to reason about and all, but it's always a way to write down. So in this particular case, in this particular example, this is the function where whenever it's 1, it's 1. And so the corresponding Boolean algebra equation is simply this: x sub 0 and x sub 1 and x sub 2. By the way, even though in the slides, usually I write it x0, you can also think of it as this guy, same thing. Okay, so it's like Depends on, like, if you're writing it, you can write it that way. Or so okay, so I can now sometimes we will just write it as f equal to this. That implies that f has x0, x1, x2 as inputs. Okay, so depends on the context. One thing I would like to just generally urge is that I mean, it's not just about this course, all of engineering. If something is, let's say, underspecified, take the most reasonable assumption. Okay, kind of don't try to defeat the intent of the problem by finding some way around, which kind of miss the letter of the problem. You may solve it, but kind of you lose the spirit of the problem. So you'll find oftentimes that, you know, there's something either something ambiguous or underspecified. Either talk to us or take a more reasonable assumption. I say that because I think in one of the discussion section, that problem about rat and poison and stuff like that, and I think one of you came up with this, the rat, I may have a clock, second level granularity, and I can then detect, because kind of made the assumption that the rat would die exactly at an hour point. So hope you remember that problem. Okay, so the thing is the following: in real life, think about it, where it's coming from, right? If someone takes poison, there's like some time of a safe window in which they are going to die, and after that they are in the clear. So that problem was sort of based on that. So kind of the intent was 1 hour was meant like as an unsafe window, and not that the rat will die exactly. If it were to die, it will die exactly at the 1 hour point. Same thing here. I mean, oftentimes you will find that I did not fully specify things. Please take the more reasonable assumption as opposed to sort of, okay. Anyways, so let's take another one. So again, we are going to think in terms of the game. The 3 inputs represent the 3 flips, and we want the player to win the game if the majority are heads. Okay, so in this particular case, we're saying 2 or at least 2 inputs are high, right? So in that particular case, this row has 2 inputs. This row has this input and this input. This row has these 2 inputs, and this row has all 3 inputs. They are the ones, the remaining are 0. Okay, so that's a function. There's nothing specific about it, although you might imagine something like this might actually be part of possibly some game that I want majority to be high. Okay, so that's another example. I can write it as a function. So when given a truth table, one way to write the corresponding expression is to write the expression for each row and then OR them together, right? Because in some senses, this is saying that I'm either in row number, if I start from the top, I'm either like row number 0, 1, 2, 3. So I'm either in row number 3 or row number 5 or 6 or 7. Okay, so I can write the equation for this function by simply enumerating each row. So that's what you see out here. This one is saying I am in row where x0 is 0, x1 is 1, and x2 is 1. So that corresponds to this row. The second one is saying I'm in the row where x0 is 1, x1 is 0, x2 is 1. And so 1, 0, 1, that's this guy. Then the third one is this, and the fourth one, all 3 are high, is this, and then I OR them together, right? I mean, I'm saying in either this or this or this or this, okay? Not the most compact way of writing this function, but it's certainly a way of writing this function. I just list, right? So I literally write the expression of the row. So I am in a particular row if the x0, x1, x2 have a particular pattern. So like, for example, I'm in row 0 if not x0 and not x1 and not x2 is true, right? I mean, all 3 have to be 0. I am in this row if not x0 and x1 and not x2 is true, right? I mean, so I can look at the input columns and say, when am I in that row? And then I'm only looking at those rows where I'm high. where the output is high. So I just list those in this case. So those are the three out here. So given a truth table, I can always write the expression, and vice versa. Given this expression, I can plug in all 8 possible combinations of the input values and fill out the truth table. And you can convince yourself that the two are perfectly equivalent. Okay, whether I do this lookup table or whether I do this expression, they are perfectly equivalent. Now, the question which will come up, which comes up is, which one is better? I mean, clearly the latter is more compact. I can write these expressions. Usually these kind of arithmetic expressions are represented as some sort of a tree data structure with operators as the nodes. If you have done some CS course, I'm pretty sure you would have seen this. So there are ways you can express the expression in a program. And truth table, obviously, we can express in a program as an array of some form, right? I mean, so both are expressible, but presumably the first one is going to take a lot more memory. I can, I don't know, can someone suggest in some programming language, how might you store this kind of a multi-dimensional array? Like, okay, Python. I'm sure most of you know Python. Anyone? Okay, so how would you store this kind of truth table in a Python? Okay, so yeah, so, well, I mean, you can use NumPy's multi-dimensional tensor, for example. Okay, so there are lots of packages already out there. There is in Python, there is a package called PyEDA. PyEDA. It's meant for Python package for electronic design automation. It actually has all these truth table and all things there, so you could use that too. There is so anyway, so a variety of ways kind of doing it, or you can just go deep down and just create a list of lists, right? I mean, you can do something like that. So anyway, for our purposes, both are equivalent. Some operations are easier with the arithmetic, with the truth table, and some operations are going to be easier with the expression approach. Okay, so let's see. Okay. Why am I sorry? Okay, so combinational systems can be expressed as truth tables. We saw that last time. Boolean functions can be represented as truth tables, which we just saw. So what follows is Boolean algebra can be used to represent combinational systems. And more importantly, since once we are in the world of algebra, we can manipulate it, we can optimize it, we can do clever things. I can say, are these two combinational systems doing the same thing? For example, I can do all those kind of things while staying in the world of Boolean algebra. I could, if I give you two circuits and ask you, are they the same thing? You can always make the truth table and compare the truth table, right? If the truth tables are the same, they are doing the same thing. But that can be, as we saw, truth tables can be huge, so huge that you can't represent them. Boolean algebra, by applying the rules of algebra, I can answer those kind of questions. So, therefore, what it follows is there are many ways we can represent Boolean functions: truth table, logic expressions, and there are some others. There's something called implicant table, there's something called hypercubes, corners, decision diagrams, inverter graphs. There's kind of a long list of them. In these binary decision diagrams or reduced binary decision diagrams listed out here, they're often used quite a bit. So let's see. Each one of these have strengths and weaknesses. We are going to spend some time going over some of these next time. Okay, so I'm not going to do that today. Just wanted to mention that almost every problem having to do with combinational logic, any problem of interest, like how do I implement it with fewest number of gates? Are these two systems equivalent? All of them are hard problems. One which is kind of like, anyone of you heard of satisfiability problem? Heard of? What is it?
Like if you're trying to solve like a puzzle, like let's say Sudoku, And you are trying to like find a solution. Satisfy all those.
So you're on the right track. Okay. So firstly, Sudoku can be expressed as a set of Boolean logic constraints. Okay. So what satisfiability problem says the following. Let's say I give you the expression for a Boolean function. And I ask you the following question. Is there an assignment for the input variables? Let's say it has 100 input variables, x0 through x99. And so satisfiability problem says, does there exist some way of assigning zeros and ones to x0 through x99 so that the output is 1? That is, the function is satisfied. Hard problem, but appears in all sort of not just puzzle solving, but all sort of real life problems. So it's called the satisfiability problem, and there are variants of it and all, but it basically says, does there exist an set of input values which will satisfy this function? Okay. So just now for our hardware purposes, of particular interest are two kinds of problems. One, I give you an expression. What's the simplest way of implementing it? Lowest cost, fastest, least power, those kind of things. That's one. Another is I give you a function and I give you a circuit in terms of gates. Are the two the same? Verification, right? Is my circuit implementing what I specified? So equivalence, right? Are the two equivalent? Okay, so these are the problems like these. They are of tremendous interest naturally when you're designing companies like Intel and all, when they're designing complicated things. So I'll give a glimpse of that when we meet on Wednesday. So we're going to stop now. And so any closing questions before? Okay, bye. See you guys on Wednesday.